Everybody. On the fourth day morning of the conference celebrating a decade of Higgs organized by Day4 Mumbai. So today morning session, we have 3 talks, and the 2 talks are basically Indian contributions to standard model and beyond standard model physics searches using the Run2 data with CMS experiment. And the third talk is on the basically SM Higgs model scenarios. So the first talk is by Professor Pralay Mal, and he will be talking on the Indian contributions in the standard model Higgs measurements using Run2 data. So Professor Mal got his PhD in 2005 from Day4, working the D0 experiment at Run, and then followed by postdocs in the University of Notre Dame and the University of Washington, Seattle, in the same D0 experiment. Subsequently, he was a postdoc in Atlas experiment associated with Sackley, and then he joined NICER in 2012 as a faculty member, and then switched to CMS experiment. And he has expertise mostly in the Higgs sector and the top quark sector. So with that, I will just hand over the stage to Professor Mal. And if his slides are shared, so please go ahead, Professor Mal.
Thank you so much, Professor Swine, for the nice introduction. Of course, so it's a pleasure, firstly, to give this talk to summarize the Indian contributions to the standard model Higgs, the contribution to the standard model Higgs measurements using the Run2 data set. And yesterday, Professor Kirti Ranjan from Delhi University has already covered the first part, which containing the Run1 analysis, where Indian groups have been involved and led the analysis to the discovery. So, so let's get started. And thank you to Professor Majumdar for the invitation to give this talk. Okay, so we all know this one. I mean, this was July 4th, 2012. And then subsequently, we submitted the paper from Atlas and CMS. And the cover page, it appeared here. And some of you who are the authors, you must have the personal copy of these. And you may also have noticed that there are this nice, letter from Peter Higgs and Francois Anglet on that paper. So here, as Professor Swine has already told, that I was at the discovery time, I was on this camp rather than join Candela site. And so I take this opportunity to disclose that as well for the people who do not know. So about the statistics, I think I had the one from Atlas, this accumulation one. I will just spend 2 or 3 slides on this, and then we go to the real topic of mine, which is the Run2 analysis. So here you can see how over the time the Higgs to gamma statistics evolved in Atlas experiment, and the dates you should notice that how it changed. And finally, we got the full Run1 data set. Also, there was another discovery channel that was this Higgs to ZZ going to 4L, and there also you have this nice accumulation over the time at operation of 7 TeV and 8 TeV, and you can see slowly over the time how Higgs statistics accumulated in this region, and you'll see that right, it will appear, and there is an excess, and if you do not put the standard model Higgs, it doesn't. It's the discrepancy. And same way later, I think this was not the discovery channel, but it's the 2012 Higgs to WW. The statistics also got accumulated the similar fashion, and those are the 3 different channels which basically had a large statistics with significant discovery potential. And the other first two we have discovered the Higgs on those, and then the third one is just for the reference. So at that time, I was just checking yesterday that okay, there was this CMS India CMS authors over there in those papers, and then I was just looking at after 10 years, one of the recent papers, that is Higgs going to CC bar, that we submitted last month from CMS, and this is the list of authors from India CMS collaboration, and you can see that the number of people sort of still remains the same here. So anyway, about the Run2 legacy, I think I already mentioned here. So the two of the channels that had the significance.
Can I ask a question?
Yes, please.
Can you go back to your previous slide, please? The number has increased, isn't that true? From 2012 to 2022.
Well, some of them are students and etc. Well,
no, the author list is what I'm talking about now.
Yeah, I understood. I understood your question.
Many people have retired.
Yeah, so I think it would be actually interesting to have this particular data. As Kajari said, some have retired, some have joined. And what is the total number which was there at that point, and what is the number now?
Yeah, I counted it, I forgot. And there we included, that's what CMS diktat was, all the people who have contributed. So that included scientific officers and technicians, etc., who helped us with it. But now for the physics papers, we have only the immunotherapy.
That is what I meant, that it is actually for the physics papers that I would be
really. Even for the discovery paper, if you see on the left side, that included more people than the physicists.
Oh, I see. Okay, so that I leave it to you. These are sort of what I would call as the fine structure. Fine structure, I understand. I can see the name of Ghodgaonkar, for example, here. I don't know whether he was or Topkar. R.K. Chaudhary on the other hand, and so I know there are these issues, but I leave it to you to make your own count and have something. It would be interesting to know what has actually happened over the years in terms of this particular set of people.
Sure.
We have been submitting evaluation of human resources to the funding agencies. So it is there. Who has gone here, where, etc. Anyway. So.
Yeah. So anyway, and another point I wanted to mention here that the Higgs paper, Professor Govinda Majumdar, I think he did not sign on this discovery paper, and because he did not believe probably at that time. But anyway, moving on. So the legacy from the Run1 was basically these two channels, the Higgs to gamma gamma and Higgs to ZZ going to 4L, and these have the significance, the discovery, we discovered Higgs in those channels. Rest of the channels we had this kind of situation, and overall the signal strength considering the standard model Higgs was something is consistent with standard model, and that is 1.09, and this is the legacy paper from Run1. And of course, you all know that in the opening session of this symposium, Vivek was Professor Vivek Sharma from UCSD were talking about this plot, and there was this KF and KV. This has to be, these are measured for 3 generations of actually 2 generations of leptons and quarks, and then they match quite well with the standard model prediction. And here is also the split up that I showed in the last slide in terms of 5 different production modes. Okay, so now coming to the topic of mine, which I'm supposed to cover here, is the Run2 analysis. What happened beyond basically the Run2 measurements. And so first to do that, so basically, as you all know, and this must have been iterated many times here in the symposium, that there are basically 4 different production mechanisms: the GGF, VH, VBF, and TTH. And at 13 TeV, the corresponding cross sections are written GGF is the highest one with the 49 pico-1 cross section. And the good part here, okay, that's in the next slide. The good part here is that this is the plot that the cross section on the left side, and right hand side you have the branching ratio of the Higgs in different decay modes. So so the cross section here, as you can see, from 8 TeV to I believe you can follow my cursor, right?
Yes, yes.
Okay, very good. So the cross section, you can see that is the 8 TeV result was the 24 pico-1 is the total cross section, while the 13 TeV you have something like 55.6 pico-1 cross section. So it has changed or increased by a factor of 2 to 4 depending on which channel you are looking at. And the good part here is that the Higgs mass is more or less known, so we do not need to go to the previous situation that this whole phase space is open or any branching ratio is possible. We have pinpointed that one after the Run1, so that means that we can strategize our measurements in certain regions, and we know that we can improve the sensitivity correspondingly, and then of course we can observe the signal, observe in the sense that the 5 sigma statistical significance over the background prediction that we can establish using the respective channels. So this was really the advantage when we moved to the 13 TeV from the Run1. Now, the other component that comes is from the luminosity. And in this picture, what I saw is the CMS luminosity over the time, over the Run2 period, 2015, 2016, 2017, and 2018. And these are the day-wise peak luminosity when the LHC was operational. And you can see that we have steadily increased the luminosity, and we have accumulated, this is the instantaneous luminosity. So we'll talk in the next slide in 2016 itself, we had the record-breaking luminosity compared to the previous projections or the design we had. And then of course subsequently we even crossed the design in subsequent years, design luminosities in subsequent years. So this plot shows actually the integrated luminosity. The left side plot shows that over the time, how the integrated luminosity, how much data we have accumulated over the time. And 2016 is here, that is around 51 inverse data that we have collected. Then 2017 we have around 50, and then 2018 we have something like 67. And then if you sum all these together, you get the overall luminosity, and which is something like the delivered. So one has to understand that okay, the LHC delivers some luminosity, and CMS because of the detector readiness, and same is valid for Atlas or any other experiment, that how much you can record, and we roughly recorded 150 femto-1 inverse of it. So that is our full data set. And it's a remarkable achievement by the LHC, the accelerated division, that they delivered this much luminosity and better than the designed one, and that made the Higgs measurements very pinpointed or more precise. Now, what are the challenges? Of course, the luminosity increase doesn't come as free. Here, so for example, the pile-up events, of course, it was in Run1 was sort of around average, was around 21. And then in the Run2, you can see that average over all the years is coming out around 34. So definitely it has increased. And of course, the 2018, there was quite high, and pile-up can go all the way to 70 or above. And Then of course the other point happened was that the bunch crossing time decreased. In Run1 we had the 50 nanosecond bunch crossing, and in Run2 we have the 25 nanosecond bunch crossing. That means electronics, we had to scan the signal much faster, and of course the out of time pile up effect will also affect the signal very heavily, apart from the in time one. So we had better handle for in Run1 to handle the out of time pile up, but in this case so that means in our simulation we had to also incorporate the corresponding bunch crossings much higher level. Then of course we had during the LS1 the whole level 1 trigger system or changed into the micro TCA readout system, and that sort of led to the fact that okay, it's faster and more advantageous, but that is also something that we had to handle, that it's working fine and so on in terms of operation during Run2. Then in between, in 2017, we had this pixel upgrade also, phase 1 pixel upgrade, and you can see that we have changed the coverage of the pixel detectors from 3 layers to the 4 layers, and that helped a little bit to mitigate the pile up situations that is worsened during the Run2. Okay, so these are so there are some pluses and minuses, and based on that, we went into the Run2. So before I really move to the analysis specific ones, I wanted to mention that I have collated some of the or most of the analysis that were the India CMS group members have contributed or have been involved, and I had made a call, but I'm open that if I have missed, mistakenly, I mean, I would be happy to include it here. So please do not take my offense on that. So the first analysis was with the 2016 full data set. This is where I think Pallavi and Professor Mojumdar from TIF, they were involved, and they led this analysis. That this is basically to look for anomalous THQ coupling, and the reason to look for this anomalous coupling is that you have this vertex and over here, and depending on the because this is as compared to TTH, this could have the signal, the sign, it matters in the interference way, and this is where the BSM physics can really sneak in, and that can enhance the signal, and that's why it's important to measure. And with the very first 2016 data set that was measured, and here basically the final states are the 2 same sign leptons or 3 leptons, and the leptonic decay of the top quarks, and Higgs is decaying here into the W, Z, and tau. So the bottom.
Can you hear me? Yeah. I want to add, like Siddhesh, when he was a postdoc at TIFR, as well as Sudeshna also worked on the TTH part of this analysis, TTH to multi-lepton final state.
That is coming up. I'm not done. I have 40 minutes left still.
Yeah. Just to add to this, besides Pallavi, they were.
I have the slides. I have the slides on that. I have still 40 minutes left for my talk. This is the very first slide for the analysis. Please allow me to move to the later stage, and I'll cover that one that is there.
Yeah, Pralay, let's go ahead. Yeah.
The final states we are looking at here is the 2 same sign and same sign leptons or 3 leptons here, and you can see that the detailed BDT training and other things have gone into here, and the most the background is the TTV and the top pairs, and those things are these are background prediction is here, and then you have the THQ signal as predicted from the standard model is here, and we interpreted this result into this KT by KV measurement, and the upper limit on jointly on this one is done. It's like because you get the cross-section limit, and that is 0.64 picovolt, and then expected is something like 0.32 picovolt, and that can constrain this KT at 95% confidence level, assuming that KV is at the standard model value, that is 1. And this was published, and I think it's part of Pallavi's thesis in 2019. So next is the Higgs going to, I'm going through, so as Ramkrishna has mentioned, there are quite a few analyses afterwards, but I'm going chronologically in the sense that the volume of the data set, that how you, for example, I first wanted to cover the 2016 data set only analysis, and then move to the full Run2 and other things. So this is Higgs going to ZZ going to 4L measurement, and SINP had been involved since the beginning of this analysis, and basically it was after the Run1. There are many important ingredients that went into this analysis. Is that, for example, the lepton isolation improvement, and then also the triggering part, and few other important ingredient that was contributed initially, because this paper is kind of something like 300 people paper within the CMS, and SINP still had a dominant contribution in terms of making the contribution meaningfully in this analysis in terms of lepton ID development, and also the triggering part taking care of that. So here the idea is that the Higgs, the QQ bar, the main background is the ZZ, the standard model ZZ background, and Z plus Jets. And if you the whole analysis is split into the three different channels, basically the 4E, 4mu, 2E, 2mu, and so on. And finally, the matrix element discriminator. So matrix element is used here because at the pattern level, you can use the diagrams and build up the corresponding probabilities that I do not want to go into the details here. And that gives you some probability to discriminate between, for example, the VBF versus GGF and so on, and also the background one. That is what is the final discriminator that is used. And in this picture, you can see that how nicely the Higgs going to ZZ going to 4L signal is sitting here, while the other standard model backgrounds are also can be observed here. And the total expected number of events is something like 1400, and then observed is around 1500, so it's consistent with standard model. And this analysis was published in 2017, and I think from SINP, Professor Subi Sarkar, Shubhankar Raichaudhuri, and Rajur C, they're the key contributor to this analysis. The final signal extraction actually happened with a 2D likelihood fit that is using the 4L mass, as well as this matrix element based discriminator that is being used here. Okay, so this analysis then calculates basically the overall signal strength, something like 1.05, and this is consistent with the standard model. And here also you can see that the results can be done or interpreted in 2 dimensions on the signal strength in GGF and GGH, and then VBF and VH in one side, the signal strength, and then TTH and these two together. If we do the 2-dimensional way, the standard model is here, and the base fit value is somewhere here, but it's still within 1 sigma. And this analysis, as I mentioned earlier, that there are different categories that it profits from, and it treats the signal and backgrounds even differently there. Moving on, the same analysis also got interpreted in terms of, or the Higgs width, one could set the limit here. So for example, in this particular case, it's a 95% confidence level. The Higgs width was constant to 1.1 GeV. And also the mass can be extracted, the Higgs mass can be extracted. And in fact, this mass was even better than what we got in Run1 combined from Atlas and CMS. Basically Higgs to ZZ and Higgs to gamma gamma combined one, it is better sensitivity than that one, and that was also extracted, and all these things basically were published in this paper. And this analysis was one of the very first important papers from the Run2 before we went for the pixel upgrade, because it has major impact later from the pixel detector upgradation and so on. So okay, moving on to the one that Ramakrishna was referring to. So the evidence and observations. So where the TIFR people, especially the Sudeshna Banerjee, then the Sawant, and then Arun Naika from IOP. All these people are involved here. So this was again with the 2016 analysis and combined with the Run1 and to find the evidence or observation for the TTH going to multi-lepton. And this result is also subsequently superseded by another analysis that I will come later in this talk. So what you can see here is that this is the signal strength of the TTH, and you can see the corresponding lines where the 3 sigma and etc. lies. So for example, this is the Run1, the red curve, and then the 13 TeV is this one, and then the combined one. Once it's combined with the Run1, you get sort of discovery or not discovery, observation significance. And then this analysis, of course, was as I mentioned, different groups are working and they contributed in different areas. For example, as I understand, the IOP professor Arun Naika, he contributed mostly on the tau side, and other people from TIF, they worked on the electronic decay of the top and its direct decays. And this finally got published in 2018 in the PRL. It was initially some publication in the JHEP and then subsequently followed up publication in the PRL. So one of the major things from CMS is to do the simplified template cross-section measurement that is called as STXS. And the reason for doing it is that it's a fine-grained measurements of individual Higgs production modes in various kinematic regions, and of course, considering the decay. I am going to cover this particular analysis simply because the SINP and NISER or Indian contribution is on this analysis. But there are also, for example, the Higgs to tau tau, there are also Higgs to ZZ, and then also Higgs to ZZ, Higgs to gamma gamma, Higgs to tau tau. The STXS analysis do exist, but that I'm not going to cover here. The idea is that we partition the data in different kinematic regions, and finally we pass it. I mean, the combination of different channels and different decay modes become easier, and that maintained across CMS the same kind of, when we say, for example, stage 1.2, that means that how many bins and etc., how many analysis modes are there, that is already mentioned, depending on the different production mode and other things. So the key analyzers are of course Professor Satyaki Bhattacharya and his team members on this analysis. I mean, he had been working since even he He has been working in Run1 and then followed in Run2. Some of the calibration for the Higgs to gamma gamma using the Higgs to Z going to EE are routinely provided by the SNP group members for this particular analysis, especially in the Higgs to gamma gamma channel. And then from NISR, we basically contributed, myself and my student Prafulla Saha worked to include this TA channel up there. Before that, it did not exist in the STXS analysis. So so that is where we are meaningfully contributing into the STXS analysis. Now, what we do in the Higgs to gamma gamma STXS analysis is that we remember this is a very pristine channel with a mass resolution of 1 to 2%. However, it suffers from the very fact that the branching ratio is quite low, and so so we developed basically the BDT and DNN based techniques to develop a particular selection for different categories of events. For example, there are trainings for the TTH, separate one that they use the DNN, and we use something based on the BDT on the TTH. But all of them, we made sure that the migration of the signals from one channel to the other happens minimally, and preserving the best sensitivity of the analysis. And finally, you model the overall the Higgs to gamma gamma peak this way, and then in the standard way as done in the discovery time, that we have a falling spectrum of the Higgs to gamma gamma, and then there is a peak. So this is signal plus background fit, and then subtract the background component, and you get the corresponding peak there. So this one, then you interpret the results in different production modes. So this is your GGH. There are 11 channels, then QQH, and the VH, TTH, and the final one. This point is basically the analysis contribution. And this one actually, if you just go back, then this is the 4 different channels, meaning the channels combined from here, they have the signal strength, and you can see that the corresponding there is a little bit of high side the measurement, but still is consistent with the standard model. I mean, not too far from the standard model prediction. So moving on now, probably this is the analysis that Ramakrishna was referring. So the multi-leptons going to, I mean, the TTH production in multi-lepton channels using the full Run2 data set. And here, basically, the TIFR group members are involved. There are also the IOP group members are involved, and the internal paper also says that IISER Pune, there are also people, and so that is a Gala contribution, and this is one of the classic papers that we had during Run2 on the TTA. In the TTH and the corresponding backgrounds, and this was this has been published in 2021 in the European Physics Journal. So so this plot shows that what comes out of this particular analysis, that the signal strength in TTH and signal strength in TH and the corresponding significances. So for example, here we have 4.7 sigma significance, while we expect 5.2 sigma significance. However, the TH or the top and Higgs, I mean the single top basically, And that has lower significance, which is 1.4, while expected is something like 0.3 there. So we can do also the measurement on so these are the further split ups. For example, there are 3 broad categories that I was talking in the earlier slide, last slide, and what the signal, how the signal strengths look like there. And this is what it looks like. And the combined number is 5.7 times. So this is on a bit high side, but you can also see the error is quite high here. And then it's a further split up here. You can see the corresponding TTH channel. What are the split ups? And they are quite consistent. They are very close to the standard model one. But TH basically is a suffering high both systematics and the statistical error is limited with that, and that constrains basically the KT in at 95% confidence level in different regions here. Okay, so moving on. So the Run2, I think one of the key papers is the Higgs self-coupling paper that came quite recently. So the idea here is that gluon going to di-Higgs production, the leading order diagrams you can see here, and then VBF, you can also see the leading order diagrams. Now the trilinear self-coupling that let's call it Higgs, lambda, and then 3 Higgses there. So it's very sensitive to trilinear Higgs self-coupling, and the idea is to measure basically this one with respect to the standard model. In the opening session, I remember that Professor V. Ravindran, he was talking about. So this was basically without the electroweak correction. But he was talking about the more measure. So this is a theoretical, you can think of that all the numbers here, and the electroweak corrections are not included here, and that can improve or improve the calculations there. He was talking about in the opening session on this particular plot. But for the CMS side, we wanted to measure this thing with respect to the standard model prediction, and also try to probe basically this C to 2V, and then this the vector boson to Higgs coupling that number here. So here basically we have the Higgs, so BB bar. So we have 2 Higgses. One is BB bar and then Higgs to gamma gamma. And here, I forgot to talk about the seminal contributions from the TIFR as well as from IISc that I think Shoumo and Professor Majumdar from TIFR are working on this month. They're leading this analysis, and Professor Jyotsna Komaragiri and her student Lata is heavily involved in this analysis as well. So in fact, TIFR and IISc, as far as Higgs to gamma gamma subgroup way, I know that they're leading the analysis here. So BB bar. So we have two different let's say peaks. One is coming from the BB bar, the other one is coming from the Higgs to gamma gamma, and the Higgs to gamma gamma one is modeled with the 5 Gaussian ones, and then the BB bar one is basically modeled with the double-sided crystal ball, and these two together, these are considered to be two independent likelihood distribution, and they're combined together, and the final fit basically is done on these 2 parameters. It's a 2D parameter fit, and based on that you can get basically okay. So in addition, while you are doing the signal plus background fit, you also use the background model that is basically the model with this exponential Bernstein polynomial and power law. Different styles are tried, and finally certain thing. The differences are also considered actually in the systematic uncertainties there. I do not want to go into the details here, but these are already considered, and based on that, we do the fit and interpret our results here. So the observed value of the K lambda is something we were range bound between minus 3.3 to 8.5, and the expected is minus 2.5 to 8.2. And in the standard model, if you just the value has to be around K lambda equals 1. And if we consider the upper limit, if we put the K lambda equals 1, then we get the upper limit on the signal strength, and that is at the moment is something like 5.7 with respect to the standard model, and then the observed value is 7.7. So we can do further interpretation of these results, which is this Higgs self-coupling, this C2 and C2V, and the corresponding measurements. You can see that 95% confidence level, we have the values something, it's consistent with our expectation that between this range. And if we put CV and K lambda equals 1, then we can constrain, or we can put the corresponding limit on this C2V, and that also is quite consistent in terms of observed and expected limits. And of course, we can further translate these numbers, assuming again the K lambda equals 1, the 95% confidence level on the signal strength, the di-Higgs production using the VVF channel. And there you can see it's not sensitive, but we have to pursue this analysis a good onset at this point of time. So moving on. So next, another important measurement is the CP measurement that was using the Higgs to tau. The idea is that so this is again using the full Run2 analysis. So so this is where IOP Professor Aruna Nayak and then his group members, they are involved heavily, and the idea is that that the Higgs is decaying back to back, and in that way, so you can think of their back to back here, and then further depending on the tau decay modes. For example, the tau is a one prong tau in this particular case, decaying to one charge pion. So you reconstruct this plane and reconstruct the other plane and calculate what is the difference in terms of angle between these two, and that has some implications in terms of the CP measurement. Because why? Because if the CP is so within standard model Higgs, it should be 0, and so we try to probe that particular feature, and here of course we have to rely on the charge reconstruction, charge track reconstruction, and the corresponding the tau identification. And this analysis actually is found to be quite sensitive in terms of the different decay modes of the tau, and that's why it's categorized in different beams. And also there is some MVA that is developed to identify different decay modes, and based on that we basically categorize, and then finally we extract the signal here. So so for example, here you can see phi of CP in degrees here, and this would be the hypothesis with the alpha h tau equals 90 degrees, and if this is the 0, that is the standard model 1, the rate 1, and this would be the curve, expected curve. Now the data is all over the place, of course, but still you can exclude this hypothesis, that is the 90 degrees hypothesis, at 95% confidence level. Okay, at 3 sigma level, this hypothesis is excluded, meaning the alpha H tau tau equals 90 degrees. And then you can calculate what is the, at 95% confidence level, what is the value or upper limit on the alpha going to HTT, and that's coming out to be around 41 degrees. So we haven't completely gone into that, but this has been a very good step towards the CP measurement, and this is also one of the key measurements from recent measurements that came up this year itself. And this one shows basically the CP even and CP odd. So CP even is a 0 degree one, and CP odd is of course the 90 degree one. And you can see the corresponding contours here, and result are shown here. So moving on, so I apologize that I could not include other details from for this upgrade studies, but as you all know, and there were comprehensive talks on that LHC is going to get upgraded, and high luminosity LHC projection studies have been already performed. And so this is the rough schedule at this point of time, and with that, at 2027 we'll have something like 3000 femto-1 inverse of integrated luminosity. We add the instantaneous luminosity would be 10 to the power 35, and with those, that means that pile-up events would be much higher, which is something like 200 or 140 or to 200. And to justify or how the physics projection studies physics would look like, or how difficult it would be at the high luminosity LHC, there had been some projection studies which had been done, and there are YOLO reports based on that. So first one was again this is from the TIFR group, Professor Kajuri Majumdar, and this is on the THQ process, and this already got this archive number here. And quite recently on the BB bar gamma gamma one, that projection studies based on what Shomo had been doing, he has also completed that FDS studies, and this is also part of the SUN YOLO report. So so with this, that brings me to, I guess I'm in time. Okay, very good. So that brings me to the summary and conclusion. So LHC Run2, we have the comprehensive picture of we have portrayed the SM standard model Higgs, the comprehensive picture, and the multivariate techniques and larger data sets have allowed us basically to overshoot or overtake the previously projected measurement sensitivities, and we are doing better than what was projected earlier. And India CMS group members are contributing significantly to steer the CMS Higgs measurements so far. So newer decay modes and the analysis and better sensitivity may be possible. Even the Run3 that's coming up next year, as I showed I did not discuss about it, but it was there in the last slide, that we'll have the Run3. It's about to start now. I mean, the LHC is operational at this point, and we'll collect that data, and maybe it's possible that we can have better sensitivities further on some more new channels. For example, I already mentioned that Higgs to CC bar is something that was not initially envisaged, but at the moment we have already communicated, as I told in one of the earlier slides, where Professor Gavai was asking me about the India CMS authors. So that paper, so Higgs to CC bar is possible, and maybe a few more things were possible there. So this was the situation. So to summarize, I think this is the key plot to me, that the Higgs standard model Higgs basically couples to all the third generation and the second generation second generation lepton and the third generation quarks, and of course the gauge bosons. And you can see the corresponding errors in terms of the coupling strength that we measured during run 1. And with the run 2, we have a much better sensitivity. And you can see actually the important piece is that this the second generation lepton is also coming, meaning Higgs to mu mu. We are also measuring, and now Higgs to CC bar, as I mentioned, is also coming up. So, and they are all consistent, and this is a remarkable, remarkable graph that 3 orders of magnitude that we are, you know, exploring, making sure, and the measurements are very consistent. With this word, I close it. Thank you.
Thank you, Professor Mal, for a nice overview of Indian contributions in the standard model Higgs sector. And now the floor is open for a few questions. And I see Kajari, you have raised the hand. I would request others to raise hands so that we can go on. Kajari, please go ahead.
Yeah, can you hear me?
Yes, yes.
Just one or two comments. This is maybe I should start with the THQ versus TTH. So TTH, of course, gives the kappa T, the coupling, topics coupling multiplier, but it gives the only magnitude, because in the rate we have the square kappa T square. Whereas for THQ process, since there are 2 diagrams involved at leading order, so through this we can get to have handle on the sign of the kappa T. So that is the importance of THQ process. My second comment was related to Higgs to BB gamma gamma studies. From IISc, Josna and her student did the resonant production of Higgs, whereas we from TIFR did non-resonant production, and in particular in the vector boson fusion model, which gives access to the C2V coupling. Regarding the future studies, what you referred to, what you showed there, that is what we did for the European strategy, that is during 2019, that's the Sarnia report. And recently, when you mentioned about Shomer's work, that is gone into Snowmass report, white paper.
Yeah, that okay, I missed it. Yeah.
That was with Neelaji.
Thank you.
That was with Neelaji.
Thank you for correcting, but that is already in the Snowmass paper. I know that.
That is what you're showing. Okay.
Yeah, thank you for correcting, and of course for the notes on particular analysis.
Thank you. Ram, you have question?
Prahlada, like one more thing to add. Besides the TTH multi-lepton, TIFR group has also contributed to Higgs multi-lepton, because one member, Siddhesh Sawant, who was basically
yeah, I would add that one as well. I would add that one. I told that it was not a deliberate omission, but if I have missed something, I apologize, and then I will include it in the final version of the talk.
Okay, Rajiv, yes, please.
This is actually more a comment, and it is aimed at everybody. Maybe you should perhaps even not call it comment, as a suggestion, and treat it as an individual opinion. But if you look at your last slide, then in that you say that CMS, the second bullet point, India CMS members are contributing the adjective significantly to steer the CMS measurement so far. Throughout your talk, you mentioned names. Actually, you mentioned most often the groups, and did not really spend time on the specific of the contribution that is. So my suggestion would be taking a particular topic in that. If you can actually give in one slide summary of the work that the individual people have actually done. It could even be that they analyze this versus that or whatever. and then what the conclusion out of that work is, then one can really judge whether it is a significant or a routine work or not. And in that sense, also at that point, you could also quote your physics note numbers that you have over there along with the author names, because otherwise it becomes too hazy to really see whether the contribution is from A, B, or C as an individual, or whether the entire group has contributed or somebody in that group has contributed along with the statement, whether that is significant or not, at least in terms of a physics note and so on. So to me, this statement appears to be more just a statement without any supporting evidence in your talk. And I think you should.
I sort of agree because that information.
And so this is not to be, please don't take it as a personal or any such thing. This is a suggestion for future that if you strive, particularly since your title was Indian participation and blah, blah, blah. So then I think the Indian participation part should be highlighted more, and the credit should be given where it is due in terms of people, physics notes, and so on. I think that would make it much more interesting from the point of, at least for an outsider like me, to figure out the Indian contribution. And
I will add one more slide then with the matrix kind of thing for this with the note numbers and then the corresponding authors, maybe, if that helps. But I thought that in a symposium, if we try to
to be honest, the kind of picture that you have in your summary slide, we have seen in many talks, and in this kind of a symposium, this particular the rightmost corner picture I have seen in many talks really. Whereas the job here was to really see how the Indian contribution helped in really bringing it there. So the final result is something we know. The only thing which we don't know is the exact nature of the Indian contribution.
Okay.
Okay. Thank you. Is there any other questions? No. I have yeah, go ahead. Sorry, there is one question coming.
Short comment for an example to what Professor Gavai was mentioning. I already mentioned a few minutes back about this Shomo's work with Run2 data in the Day4 production. So we were the people who did the VBF production and putting a constraint on the Higgs pair connecting with the vector boson pair, C2V as we call it. So that was the study first time done in LHC context, and our result was the best worldwide about a year back. And now we're using 4B analysis with CMS as better constraint. So that's a specific one. There, Shomo was the person who did it. There was nobody else. Just an example.
Okay, thank you. If there is no other questions, let's thank Professor Mal. Let's thank Professor Mal for nice overview from Indian contributions.